All right, my name is Watanabe. I am a graduate student here at UT. I'm going to talk about the ferromagnetic-based true random number generators. So, sorry, down. Just to give a little overview of what I'm going to talk about today, I'm going to kind of go in the background, the motivation first for true random number generators. And I want to talk a little bit about the difference between true random number generators and pseudo random number generators, which I think is kind of like what I was more familiar with when I started looking into this. And then I kind of want to talk about like the basic magnetic tunnel junction structure of with ferromagnetics, and then how we kind of leverage this to use the true random number generator physics and design. And then after that, I'm going to talk specifically about a specific kind of true random number generator where we leverage SOT to make some probability configurable distributions like exponential and Gaussian, which I found really interesting. And then I kind of modeled my mu-max simulation after this, so I'm going to talk a little bit more about that as well and the simulation results that I got. And then kind of wrap up with a little bit of like the limitations, the next steps for the field. As it is pretty emerging field, what I realized, a lot of the papers, the oldest one that I started reading was dated back to like 2015. A lot of the papers I cited were about like 2022 to 2024 papers. So fairly new. As you'll see, there is a lot of limitations with it and scalability issues. So there's a lot of work to be done in trying to get it to a more like standard like on-chip device. But right now it does have a lot of interesting applications, which I want to talk about. So why do we need random number generators? Random number generators kind of are like binary sequences where you can think of each bit as like a trial with a probability 1 or 0 if you guys have taken like a statistics class. So if we combine a lot of those bits together, we can create a lot of like large scale random numbers, or a lot of like things, for example, like encryptions for data security and things like that. And then also, a lot of these other applications are like stochastic computing, Monte Carlo simulations, which some of y'all are familiar with like transport modeling and things like that. We need random numbers to like simulate things like scattering and stuff like that, and that data needs to be saved kind of while we go through the simulation. So that's another way we can create some of these, use these random numbers in every day, and then especially as like AI is growing, ever increasing, we need random numbers to simulate that as well, like the neurons firing and stuff like that too. They also would use random numbers. So kind of the criteria for how we base random numbers off of how well kind of these things work is the generation speed, so how often can we create bits, and then energy efficiency, so how much energy is used per bit made, and then the quality of the bits. This will kind of be, I won't talk about this as much, but there's specific kind of like testing of how precise you can get it to make sure that you're actually hitting like the distribution function that you want. And so that there's a way to test it with some like programs and stuff that all the papers kind of mention. There's one like overarching kind of like system that all of them use to test how like good these random numbers are, and the scalability, which is kind of right now I think the biggest issue, getting these into other like CMOS technologies. So as we'll talk about later as well, a lot of the trade-offs between especially like generation speed and like the quality is a big issue. As we'll see, increasing speed usually comes at the cost of being able to like truly see, like read out the numbers well, which I'll talk about more in a little bit. But kind of that now to go on to the difference between true random number generators and pseudo random number generators. Whenever you're like coding, mostly a lot of it, like the pseudo random number generators, if you're like Python and you ask for a random number, it's typically deterministic based, like on a seed. So it's like a seed such as like a clock. So at the end of the day, it's not truly a random number, and it could be kind of be scaled back to some sort of algorithm. But true random number generators, they leverage something like with nature, something truly random. So as we'll see, a lot of the ones with the magnetic materials, we use thermal fluctuations to kind of create these random numbers. And so it is at the hardware physical level where a lot of the like pseudo random number generators are software. So it kind of there's a lot of benefits because it is like a really true number that you don't really know. You can't base it down to an algorithm. And it does actually have lower power consumption, especially when you're creating a lot of random numbers. The pseudo random number generators will actually take up a decent amount of power with the algorithms. So now I kind of want to talk about the physics and how we kind of operate these true random number generators. So as I mentioned earlier, we do use, a lot of them used a ferromagnetic-based free layer magnetic tunnel junction. So I'm not going to go too much into the magnetic tunnel junction, as I know a lot of people have touched upon it before. But kind of what, kind of the difference between like random number generators and what we think about for memory. For memory, we do want it like pretty steep. Like, so we know that remember from class, like we have the easy access of the free layer where we have these two. They're like energy wells in either direction of the free access layer where we can settle into. So you remember like the parallel state and the anti-parallel state for in plane would be 180 degrees apart. So we have these two energy wells on the opposite side of an energy barrier. For a lot of memory storage, we want this energy barrier to be pretty high so we can keep it. I mean, still being able to write, of course, but we want it pretty high so we're not, like the stability is good. But in true random number generators, we actually kind of want to lower this barrier so we can allow for thermal fluctuations to kind of kick the bit to either side. And we'll kind of see there's two ways really of generating these. One is that we actually start in one of the states and then we kind of push the system to the top of the barrier and allow it to relax into either of the energy wells. And this will be probabilistic. And then as we'll talk about more later, you can kind of tune this to a certain probability distribution. And the other one's just simply lowering the energy barrier so it's so low enough that's actually on the level of thermal fluctuations, so KBT levels, to just kind of flip between the states like very, very quickly. And as we'll see, this is kind of, this allows it to flip really fast, but at the same time, it's not really like you're storing data. You're kind of just, you would just sample it. Whereas if you had a higher energy barrier and allowed it to relax, and you could actually store these memory bits. So this would kind of be better for things like Monte Carlo simulations where you actually need to hold on to some of those random numbers you generate. But if you're trying to like sample a lot of random numbers quickly, sometimes just lowering the barrier and allowing the system to flip in between the two is actually quite beneficial. So just to give like a typical idea, a lot of the memory uses their energy barrier is about 50 kBT at least times to allow for the like stability to keep these bits. For our true random number generators, this value is a lot lower. I saw some on the level of like 12 and even lower than that when you kind of leverage some of the anisotropies as well. So going on kind of to the mechanisms which I to talk about to use for switching. So the one that I mentioned first is whenever we lower the barrier, we can do this by applying a transverse magnetic field. So as you can see, this is a PMA structure where you have it, the perpendicular one, and then you apply a field in the transverse direction. So this will do is actually, it will lower the barrier to flip between the two, allowing pretty quick switching. As you can see kind of right here, we have initially with no field applied, we have a pretty high barrier, but when you do apply it, these energy differences, like they kind of come closer in angle, which I'll talk about more in a sec, but the energy barrier decreases and you can just kind of get these thermal fluctuations between the two states. Also though, at the same time, while you do have this, as we remember when we did calculate the angle when we have a transverse field applied, is that's not going to be at a fully like 0 and 180 degrees anymore for where the field settles in, and they're going to be kind of in the plane of the transverse field and perpendicular field. So as you can kind of think, this would kind of make it harder to read out because then the tunneling magnetoresistance between the parallel and anti-parallel state won't be as clear anymore because you're not having a full 180 degree difference between the two states anymore. So it is kind of more difficult to read, but on the bright side, this does actually allow for really fast generation rate because you're just kind of flipping between the two states. You don't need to do any of like the process to set up a state, as I'll talk about more later. So this is kind of just for sampling between the two. Then here are the two other main used, I know we talked about these as well, so I won't go into them as too much detail of the physics behind them, but more just the idea. So you have spin transfer torque and spin orbit torque. And as you kind of know, these are kind of used to write and flip the field. So kind of for both ideas is that we set the system into initial, like for example, parallel state, and then we try to apply like a writing current beneath the actual switching current or right at it, kind of to push the state, as you can kind of see, to the top of the energy barrier where it could or couldn't switch. and then we'll allow the system to relax. So there is as we all know from like the Mumax simulations, it is pretty difficult to get it to the exact correct probability distribution every time. And there's going to be a lot of, that's going a lot faster than I thought. Okay, so kind of to talk about more of this now, I'll just switch over. So using the SOT, we can kind of use the switching current beneath the peak to allow for different probabilities of probability like 30 or to 60%. And as we can see, as we sweep voltage, we can get like the sigmoidal kind of fit with the curve. And so we can leverage this to make a lot of different kind of curves like exponential or Gaussian with these in large circuits. And then this is kind of my simulation. I did a similar thing, but you can't really do SOT and Mumax, so I did STT, sweeping the current density instead. And then I kind of used a different shape geometry and then turned off anisotropy for one. As we can see, this kind of will change the steepness of your curve and allow for more tunability. For example, if you use like ellipsoid, then you'd have a higher anisotropy in the shape, and then you can the curve won't go as fast up, so you can actually tune it more to what you're looking for a very specific percentage of flipping. Also, my data point's a little bit off because in a lot of the papers they do a ton of trials, but as Mumax would know, it would take a long time, so I only did 20 trials per current density. And then kind of just to go on to the limitations and next steps, a lot of the trade-offs, like I mentioned, with stability and stuff like that, and then being able to read these out when you do have the higher switching rates. And then, device variability will also change probability. So the next step's kind of improving the control of the bias, and then energy efficiency and scalability. And then here's a quick summary of kind of all I talked about. We need true random numbers to truly generate for a lot of the higher encryption and stuff like that for data security. And then we use SOTs, orbit torque, spin transfer torque, and applied field is really the main mechanisms for this. And then changing anisotropy, as I saw from that, can change the switching probability curve. Sorry for rushing at the end, but these are my sources. Thank you, everyone.